Hello everyone, my name is Yunhao Cao and I come from Nanjing University. I'm glad here to present our paper, 3 Guidelines You Should Know for Universally Slimmable Self-Supervised Learning. Now I will give a 1-minute brief introduction of our paper. In this paper, we aim to train universally slimmable self-supervised networks that can run at arbitrary weights to facilitate downstream deployment. However, we find that when we apply SimSIM to slimmable networks, the model directly collapses. When we continue to use in-place distillation, the model can converge but is still far from the baseline. In this paper, we find that the temporal consistency is the key, and we propose 3 guidelines for the loss design to ensure this consistency. Moreover, we also propose dynamic sampling and group regularization to improve accuracy and training efficiency. My presentation mainly includes the following 4 parts. First, I will introduce the background and motivation of our paper. With the success of self-supervised learning, it has become the mainstream paradigm to fine-tune from self-supervised pre-trained models to boost the performance on downstream tasks. To facilitate deployment, structured pruning is one of the most effective methods and is directly supported by most current hardware. To achieve instant and adaptive accuracy-efficiency trade-off across different devices. In the context of supervised learning, the family of slimmable networks were proposed. Driven by the success of self-supervised learning and slimmable networks, we are motivated to ask a question. Can we train a self-supervised model that can run at arbitrary weights? A naive solution is to replace the supervised loss with self-supervised loss based on the USNet framework. However, we find that this solution does not work directly after empirical studies. The model directly collapses after applying the popular SSL method SimSIM to slimmable networks. Although using in-place distillation for some networks prevents the model from collapsing, there is still a big gap between individually trained baselines. So why is the situation so different in SSL, and how to further improve the performance? In this paper, we present a unified perspective to explain the differences and propose corresponding measures to bridge the gap. We begin with a brief review of previous works. There are 2 main streams for the loss of contrastive learning. One is based on MSE like SimSIM, and the other is based on InfoNCE like SimClear. As for slimmable networks, the training process mainly includes 2 parts. One is the training of the base network, and the second is the training of subnetworks sampled from the base network. The general framework of our method is illustrated in this figure, in which the loss function is composed of base loss and distillation loss. By default, we use a momentum encoder to generate targets, InfoNCE as the base loss and MSE as the distillation loss. Also, we show that we should use an auxiliary distillation head to mitigate the impact of the capacity difference between teacher and student. Then we explain the temporal consistency and our guidelines. We hope that the gradients generated by different views of the same image will also be close between iterations. That is, robust to changes and provide consistent guidance to subnetworks. By comparing the derivative of MSE and InfoNCE loss, we can find that MSE is not robust to changes in output, whereas InfoNCE is stabilized by distances from other samples. From the figure below, we can more intuitively see the stability of MSE, InfoNCE, and momentum when output feature changes. We can summarize 3 guidelines to ensure the temporal consistency of guidance. First, the base loss is based on the relative distance, like InfoNCE. Second, the distillation loss is based on the relative distance, like InfoNCE. Third, a momentum teacher is used to produce stable guidance. We will empirically find that at least one of the 3 guidelines needs to be satisfied to make it work for the USNet framework. Next, we introduce the 2 strategies we propose. The first is dynamic sampling. We argue that it is unnecessary to introduce the training of subnetworks at the start, and the training of subnetworks should be gradual. The second is group regularization. In USNet, the early channels are used more frequently than the later channels, and hence the majority of the weights will be concentrated on the early channels. However, such a weight distribution will limit the base model's capacity. To address this problem, we propose group regularization by giving smaller coefficients to the later channels. Now we will show the experimental results. Our US3 achieves better performance than the other SSL methods in most ways, and the advantage is more obvious as the decrease of width. We also successfully apply our method to vision transformers by adopting Moco V3 as our baseline method. Experiments on ImageNet also demonstrate the effectiveness of our method, and we can observe similar trends when transferring to downstream classification tasks. And here are results on downstream detection tasks. Our US3L exceeds the other methods at all weights by a large margin. We also provide extensive ablation studies. We can see that experimental results are in full agreement with the proposed 3 guidelines. None of the 3 guidelines are met in case 1 and case 2, and the model either collapses or performs poorly. The other cases all meet at least one of the 3 guidelines and have achieved good results. We can also reach other interesting conclusions from this table. From the table above, we can see that dynamic sampling and group regularization both improve accuracy for various backbones. From the table below, we can see that our dynamic sampling can be used alone or combined with the sandwich rule, which brings improved performance for both sceneries. Finally, I will make a conclusion of our paper. We discovered significant differences between supervised and self-supervised learning when training USNets. Based on these observations, we analyzed and summarized 3 guidelines for the loss design. We proposed a dynamic sampling strategy to reduce the training cost without sacrificing accuracy. We analyzed how the training scheme of USNet limits the model capacity and proposed group regularization. Exhaustive results further show that our US3L achieves better performance on various benchmarks at all weights. Thanks for listening.